Hello everyone and welcome to the new episode of our series of solving LeetCode Daily challenges. And today we are going to solve a problem called course schedule, which has a medium difficulty. And without further ado, let's move to the problem statement. So we are given a list of courses that we need to pass, and we are also given a list of prerequisites. And each of prerequisite has a form of a condition that we need to pass a certain course before we pass some other course. So, for example, if we have a pair of 0 and 1, it means that we need to pass a course 1 before we pass a course 0. And we need to return true if we can pass all of the courses, taking into account all of these prerequisites. And we should return false otherwise. Okay, let's look at the constraints. So we have up to 2000 of courses and up to 5000 of prerequisites, and all of the pairs prerequisites I are unique. Cool, that's an important statement. So how do we solve this problem? So first of all, let's think about the following. When do we get a contradiction in our prerequisite? One possible situation is, for example, like this. Suppose we have to perform a course 0 before course 1. We need to perform course 1 before course 2. And we need to perform course 2 before course 0. So as you can see, we got like a circular dependency or a cycle in our prerequisites. And turns out it's the only possible contradiction that we can get. Okay, so how are we going to solve this problem? As you have already probably guessed, we are going to model it as a graph problem. We will represent each course as a node in this graph. And if we need to do course A before we finish course B, we will draw a directed edge from A to B. Okay, and how can we answer the question of our problem with this graph? Well, if this graph contains a cycle, then our answer is false. Otherwise, our answer is true. And by cycle, I mean any path in the graph that starts at some vertex and ends at this same vertex. Okay, so how can we find such a cycle? To do that, we are going to use a recursive depth-first search. And from now on, I'm going to call depth-first search DFS in this video. Okay, so let's think about how recursive DFS works. Suppose we are considering some vertex V. In recursion, we are going to explore all of the nodes accessible from V, either directly or indirectly. So for example, from 0, 1 is accessible directly, and 2 is accessible indirectly via node 1. If during this exploration we bumped into node V again, it means that there exists a path that starts at node V, goes through some vertices, goes through some edges, and returns to V, which is a definition of a cycle. And this is exactly what we are going to do in our implementation. So let's take a look at the implementation of our first solution, because spoiler alert, I'm going to show 2 solutions to you today. So in our method canFinish, first of all, we are going to build a graph. Usually I represent graphs as adjacency lists because it's my preferable way of representing a graph, and it works for me well, like 95% of the time. So let's see how I do that. I have a list of integers, and first of all, I resize it so that it has exactly num courses elements. And each element in this list will be an adjacency list for a specific course or for a specific node in our graph. And then I'm going to iterate through all of the prerequisites, and I'm going to add a directed edge from prerequisite 1 to prerequisite 0. Okay, now I have a graph, and now we want to run a DFS on this graph. So first of all, we are going to create an array that we are going to call visited, and basically it will tell us what is the state of our current node. And we are going to have 3 possible states. The first one is not visited. It means that we have never entered this node during DFS. The second one is visited not exited, which means that we have already visited this node and we have launched some recursion from it, but this recursion has not yet ended, so we have not exited this node. And the third state is called exited. Okay, so here is what I'm going to do. At first, all of the nodes are not visited. Then I'm going to iterate through all of the courses, and I'm going to launch a DFS from it. And in this case, the DFS is called find cycles, and it will return true if it has found a cycle and false otherwise. So if we have found a cycle that somehow starts from this current vertex, then I'm going to return false. And otherwise, in the very end, I'm going to return true. I need to make a clarification. When I say that the cycle starts from a node, it means that there is a path that starts at this node, then it goes somewhere, and then it encounters a cycle. So it doesn't necessarily mean that this starting course vertex belongs to the cycle. So, for example, in here, I could have started a DFS from vertex 0, from 0 go to 1, from 1 to 2, from 2 to 3, from 3 to 4, from 4 to 5, and from 5 to 2, and I have found a cycle. And 0 is a valid starting node for such a sequence. Okay, so now the most interesting part, how do we find a cycle? Exactly like I have told you a couple of minutes ago, if we have launched a DFS from a vertex, and then during this recursive process, we came back to our node, then we found the cycle. So we are going to check a couple of base conditions. First of all, if we have reached a vertex that we visited but not exited, it means that we have found the cycle and we can return true. Second of all, if we are currently in a node that we have already exited, then there is no need to continue our recursion and we can simply return false. Otherwise, we are going to set our current state as visited not exited for the current node. We are going to iterate through all of the neighbors, and if we have found a cycle from this neighbor, then we'll return true. Okay, suppose that this didn't happen, then we are going to set our state for this vertex as exited and return false. So an interesting question is, why do we need 3 states here? Why it's not enough to only have not visited and exited? And to answer this question, let's look at the example. Suppose we have launched our DFS from vertex 0. So from vertex 0 we can go to vertex 1. From vertex 1 we can go to vertex 3. And basically currently our visited array looks like this. So it's true, true, false, true. Okay, then we have visited our vertex 3. We will come back to vertex 1. There is no more left to go. We will come back to vertex 0. And from 0, we can also go to 2. So now we have visited vertex 2. And from 2, we can once again go to 3. And since 3 have already been visited, it looks like we have found a cycle. However, as you can see, there is no cycles in here. So it's really important to maintain 3 states, because if we have reached a vertex which we visited but not exited, it means that there is a path that is starting at this node and also ends in this node, which is a definition of a cycle. Okay, so this is our first solution. And in the yesterday's video, I kind of teased the concept of the topological sorting. And now they give us a topological sorting problem for the second day in a row. So I just have to talk about it. So what's a topological sorting? So a formal definition goes like this. Topological sort of a directed graph is a linear ordering of its vertices such that for every directed edge from vertex u to vertex v, u comes before v in the ordering. So yeah, it sounds very formal and it's not maybe clear. So what do we want to achieve with topological ordering? We want to order all of the nodes in our graph in such a way that if there is a node from, let's say, node A to node B, our node A should be earlier in the list than node B. So for example, if we have a graph, a very simple graph from two vertices, and there is a node from vertex 2 to vertex 1, then our only valid topological ordering is the list of 2 and 1, and 2 goes before 1. Okay, so it's very clear. And the classical problem for the topological sorting is actually this specific problem that we are solving. So we have a list of tasks and or courses in this case, and we need to finish some courses before some other courses, and we want to find an ordering of passing of all of these courses, or actually saying that it's not possible. Okay, so how can we do that? Once again, we are going to use a recursive DFS. Okay, it's probably this solution. Second, yes. Okay, once again, we are going to use a we are going to use a recursive DFS, and we need to think about how DFS works. Suppose we have a DFS from some vertex v. When we exit the DFS of v, it means that all of the vertices that are accessible from v, either directly or indirectly, once again, are already visited. Now let's do the following. Let's maintain a list of our current topological ordering, and I'm going to go through this code in details slightly later. And when we are exiting our DFS, it means that all of the, as I said, all of the vertices that are accessible from V, we have already visited them. So at the end of the DFS of V, let's just add V to the beginning of some list that we are going to call topological sorting. And I'm stating that this way, in the end, if the topological sorting at all exists, then we will receive a valid topological sorting. Let's take a look how it works on the example. So suppose we have this list top sort, and at the beginning it's empty. So, and suppose we are launching a DFS from 0. So from 0 we can go, for example, to 2. And from 2 we can only go to 3. And from 3 we can't go anywhere. So now we are exiting the node 3. Let's add 3 to the beginning of our list. Now we are going back to 2. From 2 we can't go anywhere else. So now we need to add 2 to the beginning of our list. And as you can see, our order is correct. 2 goes before 3. So now we are going back to 0. From 0 we can go to 1. So we are going to 1. And from 1 we can go to 3, but we have already been there. So we can't go anywhere else from 1. So let's add 1 to our list. And now we are going back to 0. And from 0 we can't go anywhere else. So let's add 0 to the beginning of our list. And one possible topological sort is 0, 1, 2, 3, which is correct. The other correct topological sort is 0, 2, 1, 3, which also doesn't contradict any of our rules, any of our edges. Okay, cool. So does topological sorting always exist? No, it doesn't. It doesn't exist in cases when we have cycles. So in here, there is no way to order edges in a way that we don't receive a contradiction. And that's actually what we are going to check in our code. So let's go and check out how I implemented it. Okay, so first of all, I've built the adjacency list. Here in the visited array, we can only maintain two values. Either we have visited a node or not, and we are creating our topological sorting array, and we are calling a DFS recursively from every node. And in the DFS, we do the following. We check if we have visited the node. If we did, then we return. Otherwise, we tell that, okay, now I have visited this node. I iterate through all of the neighbors and call our build topological sorting function from the neighbor. And in the very end, I add our current node to the end of our topological sorting array. And I add it to the end only because of like complexity concerns. When I have launched all of my DFSs, I will reverse my topological sorting array because, yeah, as I've said, I'm adding these values to the end while I was supposed to add them to the beginning. So now I need to reverse it. And now I want to like solve my problem, to return true if there is no contradictions in our topological sorting and return false otherwise. And to do that, I'm going to maintain a set of courses that I have already seen during the topological sort. And I'm going to iterate through the courses in the order of topological sorting. I'm going to add the current course to the set of the scene vertices. And then I'm going to iterate through all of the neighbors of this current course. And if I have already seen my neighbor in the topological sorting, it means that my neighbor is supposed to be past this neighboring course before my current course. But this edge actually tells me a different story. It tells me that this neighboring course is supposed to be passed after my current course. So we have a contradiction and we return false. And in the end, if there are no contradictions, we return true. Okay, so what is the complexity of our solutions? In both cases, we simply run some DFS, and the complexity of DFS is big O of n plus m. So the complexity of our solution is big O of n plus m, where n is the number of edges and m is the number of, n is the number of vertices, m is the number of edges. Okay guys, so thank you very much for your attention. I hope you enjoyed this video. I tried to make a very detailed explanation. If you liked my content, please press like, subscribe, and come back tomorrow for the new video. Thank you very much guys, have a nice day, bye bye.